The confines of time have conspired to tie and twist our destinies and fate together. Because in this moment, we find ourselves together, staring into each other's mouths. And yeah, we're back again for another daily video for LeetCode. So the suffering never ends. And I'm going to keep it a buck thowie. I don't know if it's suffering. So, yeah, I would say the first 120 days, 100 days, that was torture. Yeah, I'm pretty sure that the devs hate humans. So, yeah, the first 100 days of LeetCode, algorithms, and I mean, I started a year ago, so it technically doesn't count, but yeah, it kind of sucked, but now it's kind of fire. So I've been having fun trying to figure out this problem recently. It's just been a very interesting thing to think about. I was reading a Hacker News post about this guy who pretty much was a musician. Well, he's not a musician, but he wanted to make music, and he struggled to make music for years. And he realized, pretty much after struggling for this entire time, that to become a musician, he had to become a robot. So it was the literal act of showing up every day and pretty much grinding this thing out, which sucked pretty much. But eventually he was able to create output, and then once he started just pumping out music, so pretty much he would just make like 30 songs a day, or something like 5 or 10 songs a day or something like that. And then eventually he pretty much had a realization that, you know, eventually the work output, I mean the time it takes for you to make something becomes, you know, shorter, and eventually it really becomes like a transaction. You trade, you know, a bit of time for something that lasts forever, pretty much. So pretty much the work, the duration of the work is transient, but the output is forever. So that's always something to work towards, and it's definitely something that I'm feeling. So yeah, I mean, we're not nowhere near close to the Grandmasters right now, but yeah, they're afraid. So I was talking to a Grandmaster the other day. He said I had to be stopped. So the hyperbolic coding chamber, we are growing in size. So yeah, we're coming for all the Grandmasters and their Discord. So they should be worried. And yeah, just an interesting thing to think about. So yeah, I definitely been feeling like that. So now that we're pretty much deeper into the grind, I mean, the output is more than the output is more than the sum of the effort now. So it definitely feels like something that is giving back to my brain. So all is well that ends well, but what's not ending well has been Island Eagle's attempts to attack my pronunciation and mechanical movement of my jaw. So how can a clam cram in a clean cram can? That's a good question. But a better question for someone incapable of saying these words. But always appreciate the comments. Feel strong, man. Grant Montgomery says, highly recommend using another language for LeetCode. I've had questions in online assessments and interviews come up involving heaps, priority queues, and it's difficult to implement in JS/TS. I used to only use JS/TS because it's the only language I've used professionally. That's deep. But now I use Python because of the heap queue library. Java isn't a bad choice either because it comes with a priority class queue out of the box. Facts. This is true. Yeah, I thought about switching to C++, but yeah, it's just been very interesting. I thought about switching to C++ because we're running into the same issue you're mentioning here, especially when, for example, JavaScript doesn't have a native implementation of a queue. No, not of a queue, of a deck. So whenever we write a depth first search, the time complexity is always like crazy because pulling a node off the queue ends up taking n squared time, and the worst n time, or linear time rather than constant time. So I end up having to pull a node off the front, which ends up shuffling all the nodes down, which is kind of a mess. So I'm hoping that my plan for this is to take it a step further. So I plan to bolster my memory with native implementations of all of these data structures and commit them to memory. Now, there may be no point in doing this, but I think that the individual building blocks, or the sum of the individual building blocks, are maybe the foundation for remembering large algorithms. So that's kind of what I found to be true for me. Whenever I memorize an algorithm, it always makes it easier to understand the next algorithm, because there are parts you can just, toss away. For example, if you had to explain how tennis worked to someone who's never played or never seen a racket sport, it's kind of hard to explain. But imagine explaining tennis to someone who plays ping pong, or who plays like cricket. I don't know if that's a racket sport or not, but it's just easier because there's some parts that you don't have to explain. And I feel like that's how it is with algorithms. So I want to try and learn. This week we've kind of already started. So I've been learning Dijkstra's. It's pretty much committed to memory, and now I'm trying to commit my comments to memory as well. So I've kind of been doing that and adding comments and going through, and then I'll regurgitate it with the new comments. So pretty much I'm committing it to memory in ways that I understand, rather than just committing it blank to memory. But some we will commit blankly to memory, because I don't know if it's important to deeply understand all of them. But who knows? And yeah, I've been thinking about output and where I would like to be at the end of the year in terms of LeetCode. And by the end of the year, we would like to have solved 1,000 problems. So 1,000 problems, that seems unlikely, especially since we've only solved like 180. At best, we could maybe do, if we're at 180 right now, maybe we could do 360. But I'm hoping for exponential increase in speed, which is kind of what we've been seeing in regard. No, actually, no, it's not what we've been seeing. We've been seeing an exponential decrease in speed. So it's hard to know, but I'd like to do 1,000 problems. We shall see when we get there. But what we shall also see when we get there is the result of the grind. So it'll be interesting to see. I'm hoping that on I said the end of the year, but I meant when we reach day 365, it would be pretty cool to see how much progress we've made. But I also never made the 100 days of LeetCode video. At this point, we're not making any more videos that aren't the daily videos. It takes a lot out of me, but it's taking less. So good things all around. But what's not taking less? That's a hard segue. What's taking more? What's taking less is the commission that I've been paying, the great guests who've been joining in the Discord. That is not taking less. So yeah, on Friday we had Adam Sandler in the Discord. It was a stream. Everyone in the Discord we were just hanging out and asking him questions, and it was a great time to be there. And so if you want to be there the next time Adam Sandler pulls through, you're going to want to join the hyperbolic coding chamber for that, right? And you can ask him all sorts of questions about dynamic programming, standard library, as well as C++, and pretty much everything related to programming. So you're going to want to join the hyperbolic coding chamber for that. And yeah, I'm going to be jumping into the LeetCode. So I've been doing a lot more thinking, a lot more supplemental reading, and we are still on this problem named ones and zeros. But I can tell you, the amount of progress we have made in this problem is crazy. That is because this is my worst type of problem, which is dynamic programming, and we've made leaps and bounds in our knowledge set of these types of problems. So I'm doing a lot of reading on dynamic programming, specifically in a kind of way that I'm trying to do it. And things have changed. So before I started this problem and after this problem, I am not the same programmer. So I think we're getting closer and closer. The code is shrinking in size. The random walk is becoming more of a calculated guess. And I think we should be able to solve this problem. My original estimate was by 2032. I'm thinking now the original estimate is coming closer to 2026. So we'll get there. So yeah, I don't think we'll spend another week on this problem, but I think we're so close. So we're going to get there. So I've been trying to avoid spoilers on this problem. And yeah, also, yeah. So we're going to jump back into it. I have some more things to try. And we're just going to jump into today's session, which is going to be an hour and 30 minutes long. Long like Donkey Kong. So here we are with ones and zeros. Yesterday we stopped right, and our parent tree was looking a little bit suspect. We had 5 and 3, and our expected was 4. We're getting infinity. We're actually not returning anything. We're just returning this nonsense right now. But if we look at the parent array, actually I should read the problem. You're given an array of binary strings, strs, and 2 integers m and n. Return the size of the largest subset of strs such that there are at most m zeros and n ones in the subset. Set X is a subset of set Y if all elements of X are also elements of Y. So you can see we have a string of binary, an array of strings represented as binary. We have 2 integers m and n, 5 and 3. We want the largest subset so that we pretty much have at most m zeros and n ones in the subset. So the longest subset, or the largest subset that we can create, is 4 elements, right? And it's 1 0 0 0 1 0 0 0 1 and 1 and 0. So the answer is 4, right? So we have 1 0, right? Because 1 0, 1 subtracted by 5 zeros, we have 4 zeros left, right? I mean, we have 3 ones allowed. We used one of them, so we have 2 ones left. We used 1 0, so we have 4 zeros left. We used 3 zeros, right? We have 1 0 left, and then here, right, we use 1 1, so we have 1 1 left, right? And then we use 1 1 and 1 0. A little bit complicated to say. Pretty much, we're being allotted an amount of fuel, and we want to see how far we can go given this fuel, or the longest we can go given this fuel, right? Because once we take these 4 paths, right, once we take these 4 nodes, we don't have any fuel to take this one, right? And so we have the same thing here. We're allowed 1 0 and 1 1. The longest we can go is 1 node here and 1 node here, right? So the output is 2. If you take 1 0, you'd use up all your fuel on 1 node, and that's not the largest subset. So I'm sure there's a native DP way of doing this with just an array, and you pre-compute the subproblems to build another problem and solve that one or something like that. But I'm aiming for a graph-based approach here by turning the array into an implicit directed acyclic graph. Then we're going to run Dijkstra's on top of that, because I think this is a more portable solution. Whereas the native DP solutions always seem like they don't seem very generalizable. But I don't know, I'm a noob. I'm just saying that. So if we look at what we're producing here, we have a parent array, which is what we're using to find. So Dijkstra's, right, can produce up to 3 different things, up to actually just a couple different things, but the parent array is what we use at the end to pretty much check the paths, right? And what you do is you just follow the nodes up through the array to figure out the path. It sounds a little bit convoluted. -1 means you have no parent, but 4 here means that the parent of index or vertex 1 2 0 1 2 3 4 5 6, the parent of vertex 6 is actually 4. So we go 0 1 2 3 4 to 4. Index 4, the parent of index 4 is index 1. So we go here to 2, right? And then we say the parent of index vertex 1, confusing. The parent of vertex 2 is index 2. So go 0, 1, 2, and we go to parent of this one is 3, 0, 1, 2, 3, and we go to 0 here. The longest path, so we pretty much change Dictris to make the longest path, and we pretty much do end up going through the whole thing here. The problem is that this breaks the ordering of the graph. Our output is supposed to be 4 here, but just like that tree we just saw, we have 1 node here, 4, then we go to 1. That's 3 nodes, then we go to 2, 0, 1, 2. That's 4 nodes, then we go to 3, 0, 1, 2, 3. That's 5 nodes, and then we go to here, that's 6 nodes. So we go 4, 2, 3, 4, 5, 6. That's way too long, right? So it's not the wave. And I think that's because we pretty much had an adjacency list of edges we created, right? And this looks like spaghetti code. I'm going to close the problem because we don't really need it to show anymore. We pretty much have it ingested. And I'm going to make this just easier to read. And this is a mess. So we create these edges, right? This list of edges, but we end up with, right? We want to have two special things, right? We want to create an artificial start vertex, right? Because you want the longest path through the graph, right? If we use the graph as is with just the vertices given to us by the strings here, it's hard to get the longest path through the graph because we always start at this vertex here, which may not always be the best start. So what we end up doing is added a fake start vertex with a weight of 0 that is connected to all the other nodes except the artificial end vertex, which is what we're trying to get through. And then the longest path will be represented by the tree. We can follow up through the 6th vertex or the 5th index in the parent array. As you can see, all the other vertexes 1, 2, 3, 4, and we're missing one for 5. Where's 5? Oh no, I didn't scroll down far enough. Right? Four, right. 2, 3, 4. 2, 3. Then we have one too many nodes here. 1, 2, 3, 4, 5, 6, 7. Now, where is 6 coming from? 0, 1, 2, no, 1, 2, 3, 4, 5. Right, so we'd have 7. We want every node All right, now this looks like it makes way more sense, but there's no need for 5 to have an edge to itself. It should just be we don't want any self loops here. So index cannot equal distance dot length minus 2. Why does it have a problem with me putting that? Oh, right. I guess if you start. But this line shouldn't even be necessary. Now your properties of undefined reading length. I equals, I'm not following. I is equal to 1, I is less than. We have 7 to 6. I think what we want is this minus 2. I'm not following why this is an issue. There's 7 elements. We map through all the indexes. Distance dot map. Oh, I see. Index is less than. All right, so this looks ideal. I just need to remove this last. No, wait, we're missing something now. I see. This should be 6. And then we can do one more, edges dot set distance dot length -1 to an empty array. I guess we could have just did that up here. So now all the vertices that actually exist in the strings array have an end vertex to 6, have an out edge to this arbitrary last index. This artificial last index, and the last index has no outgoing edges. That is ideal. Zero, 1, 2, 3. Right. And then the final thing we have to do, which is kind of nutty in and of itself, just because this is not actually a DAG, because there are some there's cycles. So even right, so we have a node from we have edge to vertex 4. We have an edge to vertex 4. 4 has an edge to the end. Edge to 5. Go up the tree till I count and break the rule. Okay, so we start. So the parent array says we're starting at the parent of the final artificial index is 4, which is the 0. And the parent of that one is 0, 1, 4, which is index 1. So 1, 0. Parent of that one is index 2, 0, 1, 2. So this answer is already wrong. Or it is the longest path, and you can just go through while making sure we don't pretty much include every number that doesn't decrease. Yeah, but then we end up into another paths problem. It doesn't make any sense. Let me check case 2. So for 2, right, our parent artificial index is 2, which is this one. Then we go to 1, and then 0, 1 takes us to 0. So we pretty much go through all of it. Let me check the graph that's created, at least for this one. Case 2, because it's a smaller case. From artificial index, you can go to any of the other indexes. Wait, 2. The artificial end vertex has no edges to anything else. Okay, index 1 has edges to pretty much 2 and 3, as well as an edge to the artificial end vertex. Two, 1, 3, 1, 4, 0. 2 has an edge index to the end, which doesn't make any sense because it should still have an edge to 1. 3 also has an edge to the end. So our edges still don't make any sense. Also, we don't need to even use these as any's here. The edges don't make any sense. Ideal edges would be that 1, 0 has no edges to either of these because it would end up breaking the rule, and then 0 here would have an edge to 1, and then 1 have an edge to end, and that would be the longest path. feel like a path, oh, plus another thing that doesn't make sense. The weight here for 1, 0 is 1. Oh, no. The weight here, if we need to know, we actually don't even have any that are connected to it. But the weight for 1, 0 would be 2 because it's the string length. It doesn't make any sense. If we want the longest path, we need something that can represent the fact that something that I've returned yeah, we need an edge weight that has, using the strings.length is ignoring the context of the problem, because when we do the longest path through the list, the longest path gives us something with that includes 1, 0, even though the inclusion of this would not be flames. I think we need, basically what I'm saying, I think the edge weight we're using is too one-dimensional. What if we use an edge weight where we take the sum of m plus n, which is the amount of stuff allowed, zeros and ones allowed, and pretty much we use this function that we came up here, which was calc weight. It pretty much takes, I need to rename these, and we'll just pass in s, which is a string, and instead of doing something like this, we'll just pretty much just take the subtraction of it, or we'll just take the difference, right? Instead of initial n and initial n, we'll just do m and n with zeros and ones, and then we'll just call const zeros, ones, get zeros and ones on the string s. That way, if a path, if a string, if we can't, if subtraction, if taking a path would make us use all of our would take up too much of our fuel, basically, of the allotted zeros and ones, so much that we go over, then its weight would be negative infinity, so we pretty much never choose it. So to simplify this whole thing here, we can just say calc weight m n, and then just use stir sub index -1 to get the actual weight. And I think that should help. Go to case 2. We can now see that the weight of the weight of those are still the same. Because it wouldn't really change too much there, but for the first case, the weight should have changed. And then I think the final thing we need to do, we need to employ some sort of linear ordering. We need to employ some sort of precedence on the edges so that it can actually make sense, so we can actually get a DAG. The only thing that makes sense is the m and n, right? The weight being the sum of the m and n minus the zeros and ones it would take out. And I think the way we can do that is by doing a DFS. This is just really, really ghetto. But at the end, I think this is I think if we can do that, then this could make sense. These are the edges that you would get. So I think it would take n squared time to pretty much generate the DAG. So I think we'd need a queue, for which we'd start with index 1. As well as a visited set to make sure that you can't have an edge to a node that's already been visited, which would make this a DAG. Let's say while q dot length does not equal 0, we're going to do vertex equals q dot unshift. No, unshift adds to the front. I think it's shift. Yeah, shift is going to remove an element from the front. We're going to create edges for it, and then we're pretty much going to right. So now when I say create the edges, we can do that here. This is pretty much created by neighbors. These are the neighbors. Then the BFS, right? And if vertex, if visited, right? If we haven't seen this vertex before, well, I guess if we have seen this vertex before, we're just going to continue. Otherwise, we're going to do visited.add vertex. And I think we can actually remove the loop. We don't need cur_len. The neighbors. We need to fix this line, but first let's finish fix. It just based on that make no sense. Then we have the neighbors. And then we just need to push the rest on to be processed. So here we can just say for const neighbor vertex, right, of neighbors, we're going to do q dot push neighbor vertex. And then at the end, we can push that extra edge onto that extra edge to that artificial vertex. I don't understand what's happening. Why is a vertex disappearing? We go to 0. They were try to visit our third neighbor, but its edges don't exist in the edges adjacency list. So one has an edge of 2, 3, and 4. Wait to 1 being 1. Being 1 and the edge to the artificial end vertex. Then we have the same thing for 2. We have the same, we can travel to just that next vertex. And then for 3, the only thing we can travel to is the end, which makes perfect sense. You can't travel to yourself. Two, 0, 1, 2, which is good. 0, 1. Okay. What do we have the result? So before we go to 4, 0, 1, 2, 3, 4. Then we go to 3. One, 2, 3, 4. Started this one. Oh, we go to 4. So 0, 1, 2, 3, 4. Then we go to 3. 0, 1, 2, 3. Then we go to 0. Huh? Parent of vertex 7 is 4. 0, 1, 2, 3, 4. Parent of vertex 4 is 0. So from this one, So you go 0, 1, 2, 3, 4. 2, 3, 4. We go to 4. Parent of that index is index 4. Two, 3, 4, and 5. Vertex 4 has edges to 5 and 6. 6. Vertex 3, 1, 2, 3 has vertexes to 4 and 5. 2 has vertexes to 3, 4, 5, and 6. 1 has vertexes to 2, 3, 4, and 5. So vertex 4 equals V. Longest path, a piece, go to vertex 7. The parent of vertex 7 is vertex 4. Parent of vertex 5. God, this is so confusing. The parent of vertex 7 is 4. Equal 4. Parent of vertex 7 is vertex 4. On 0, 1, 2, 3. Distance dot length minus 1 while parent sub I is not equal -1, and we'll have count equals 0, and we'll return count plus equals 1, and then I equals parent sub I. Yeah, I'm pretty sure this is still wrong still. Three and 4. Because it really should be CT minus 2. Here we ended up just dagging it normally. I think we still have to do something. I think we just have to do something like we said earlier, where in this graph you're just connected to stuff. So 1 connects to 2, 3, and 4. 2, 3, and 4, even though it's impossible to actually be connected to them. So what we need to do, we can turn this into a block. And we can just return this group all together. And then we can do something up top where basically figure out which ones you should be allowed to travel to do that. You know that if we subtract the zeros, I mean the ones here from, wait, no, if m equals 9, yeah, you would be able to travel to all of them. So let me add a test case. Actually, we can see here with this one too. So vertex 1, you can travel to 2 and 3. See, that's where the other thing, that's not possible. So we're still right. M and N are 1 and 1. Add them together, you get 2. If you subtract these, you have 0. So you should only, let's just say it was 3, we should only be able to travel to vertexes for which your weight is, the candidate vertex's weight is less than or equal to the subset left. Equals, so we have to get zeros and ones for vertex minus 1, right? Actually, we can get remaining just by doing calc weight m n and stirs sub vertex minus 1. And then for this one, we just have to do index minus 1. And then for you to have a weight, for you to have a path to it, all of these must be true. So we can't have visited it before. It can't be the start, it can't be the fake start or the fake end. And the remaining weight, the candidate weight, must be less than or equal to the remaining weight. So if we have 6 left and the candidate weight is it's not that simple. The current one would let us have this many zeros and ones left. Let's just say m is equal to 3 and we had 2 1s. We'd have 1 one left. So I think we need to do what we we're going to do earlier. So we get V zeros for the vertexes zeros that we're processing, and then V ones to get ones and zeros for stirs the vertex. That's one. Then we can say remaining M equals M minus V zeros. Remaining N is equal to N minus V1s. And then we need to do the same thing. Instead of getting V zeros, we'll get C zeros and C ones, because we want to get the candidate zeros, the candidate vertexes zeros and ones for index minus one. And then if V zeros, so if should say remaining Z and remaining O. So if remaining O, so if we have 4 remaining zeros, right, and our candidate string has 5 zeros, if remaining O's, remaining Z's is greater than or equal the candidate vertexes Z's, and remaining O's greater than or equal to the candidate ones, it's easier to just put this out here since we keep getting based on order, issues based on order. I think we just need to make sure that every vertex gets at least an empty array. Or we can also just use oh my god, this is so ghetto. Let I is equal to 1. I is less than distance. Actually, we can just do it up here. If vertex has been visited, and then we'll do something else. We'll say if edges, if we don't have any edges for it, we'll just set it equal to an empty array. Actually, it's probably not possible. I think we need to do what we were originally going to do, which is just, it is what it is, that I equals 0. I is less than length minus 1. I plus plus. We'll say if we don't have any edges for the vertex, then just do edges Not set I to an empty array. Now I'm thinking, wait, remaining Z. Our edges are still borked. Let me see if we go to case 2, which is the simplest to understand. We now only have an edge from 1 to n, and none of the other vertexes have edges to each other. So I think the way that we're doing this is incorrect. Why would that be happening? If we look at this one here, we did 1 minus 0. Also, I just realized it should have an edge with the right. And then the issue that we are facing is that now nothing has an edge to anything. So that's kind of an issue because the way we're doing it, if we have 1, 0, you get the zeros and ones, you'd have 1, 0 and 1, 1. We do m minus this, m minus that, you'd have no edges. That's true.
Oh my god, I just realized this should be distance.length. Oh my god. Parent of this let me check. I'm saying the parent of the candidate vertex actual value at the index. The most important test case is passing now. But now the other ones aren't passing. Or maybe it should be -1. Two, 0, 2, 3. Go to vertex. The best you can do here is 3. Our output is 3. I see. So it's actually a fluke that is correct. It doesn't actually mean it's correct. What's actually happening is they're just going through the entire graph, which is not ideal. And if we look at this one, two, the path we take even makes sense. Pretty much go pretty much go 2 1 0. Even the path we take here doesn't make any sense. Now that we fixed that issue, I wonder if we just change if we made this like this again. Commented that part out. Nah, because these edges make sense. Maybe what doesn't make sense are the weights. We commented this part out, duplicated it, and then went back to string length. Then up here, we'll do the same.
Yeah, I think we might just have to move on from this problem. I don't know if we have enough intuition, but we learned a lot, so I think we're just going to resume schedule going forward.